All right. Well, welcome y'all. End of our first week. So usually at the end of every class, I'll have some kind of logistics, kind of details for you all. So reminder, do that financial aid activity thing. Make sure you get that done. One is worth some points. Two, financial aid. Next is a couple students noticed that there's some typo in the problem sets. So I uploaded the updated versions. My problem sets, specifically some of a couple of answers were incorrect. So the problem sets were pulled from OpenStax, the problems I pulled, and I pulled their solutions as well. I've been unable to kind of go through and double check all their answers. Unfortunately, they have some wrong answers in there. So my hope is to get ahead of it and double check that. But if at any point you believe that there is a typo, let me know. If you do find that one of the answers is wrong, I'll be certain to reward your efforts and give like some extra points for the next quiz or something. And whenever that happens, I'll let you all know. So when you go and download, if you're working on the problem sets, make sure you download the newest version of them, just because there is a couple of answers that are wrong on them. So otherwise, so their discussion sections are going to start this next week, so just keep that in mind. Your first quiz will open sometime today, I believe. So after we cover all this units and vector stuff, we're going to finish that today. You will have everything you need to know to basically start working on those problems if you haven't started already, on those problem set problems. And then you need to finish that quiz that's going to be on units and vectors by Saturday, not tomorrow, but the 20th. So you have a week and a day for every quiz. So basically, after we finish covering the content, you have a week to kind of make sure you practice problem set problems and then start engaging with it. My recommendation to you all is that you start the quiz by at least Wednesday or Thursday. So that way, because remember, you get 2 attempts. After your first attempt, you'll be able to see which questions you got wrong. You want to give yourself time to be able to figure out how to get those right. If you wait till the last day and try to just cram it all in, you are kind of shorting yourself in some ways. Now, this first quiz isn't going to be too bad, in my opinion. Units and vectors is basically fairly straightforward. It's not too bad. It's going to get more complicated. The problems are going to have many steps to them, and you're going to need time to kind of figure that out. Yeah.
Do you recommend a scientific calculator? Can I just use like?
You can use any calculator you want, though you need at least a scientific calculator. You need at least one that has sine, cosine, tangent, that kind of thing. And then, you know, the sky's the limit, graphing calculators. So I use a graphing calculator in front of you all, not because I use any of the fancy graphing functions, but just because graphing calculators traditionally, when you hit enter, one of the most useful things a calculator can have is letting you see what you typed in. And then you can double check your work with that. So whatever calculator you use, make certain it's one you're comfortable with, and also make certain it lets you see what you typed in. So after you hit enter, make certain you can actually see what you typed in, because it's you already seen me make math mistakes in here. You're going to see me make more math mistakes in here. Anytime you all plug something in a calculator, that's a chance for a mistake. Anytime you all write down an equation, there are so many chances, so many steps in these things, and each step is a chance for a mistake. So you need to double check your work. That's super, super important in this class. When you all finish your quizzes and tests and all that jazz, so quizzes, before you submit it, double check your work. If you finish the test early in this class, double check your work. I can almost guarantee you that if you double check your work, you will find a mistake, at least in the test. There's enough questions, but the probability is just very high that you made a mistake somewhere. It's gonna happen. It's just a roll of the dice every time you do it. There's a statistical chance that you're accidentally do something wrong. It's the human condition, y'all. No one is perfect. So, pro tip, it's not fun. I know you want to be, when it gets near the end of the test, you just want to turn it in and be done with it. Push through that last little bit. It's worth the extra time and effort. Every single time I pushed myself, so when I was in school, near the end, same thing. I didn't want to double check my work, but every time I did that, I always found a mistake. Every single time. Alright, so we're going to finish up vectors today. It shouldn't take us too long. We're going to be adding them together. We didn't talk about that. We just talked about vectors last time. So last class, we basically said, hey, vectors, they have a magnitude and a direction. And we said we can break them into their components. That's a critical step that we're going to have to do. We're going to break them into components. We're going to see today why we have to break them into components. So we learned that we can break them into components. And then we also learned that we could go backwards. If we had the components we can get the total. So you can go both ways, and it was all about triangles. So we're going to see today why you have to break them into components. It is a critical step. Anytime you have vectors and you're combining them, we have to have their components. So let's get into that. So adding vectors, we're going to first do it the easy way, which is visually. This is a nice way to check your answer. So the trick to adding vectors visually is first checking what your vectors look like. So we'll have, who cares how many vectors, but we'll just start with the simplest. Let's say 2. So to do it, we're going to draw our first vector, then draw the second vector. So we got both our vectors there. It doesn't matter which one you pick with here. So I'm adding R1 to R2. I'm going to show you the order here doesn't matter. I'm going to go ahead and draw R1. Not as chunky as that, but there's R1. The more accurate your vector is, the better. So there's R1. And the trick to adding it visually is we're going to take R2 and we're going to start to draw it. It's called tip to tail. So where R1, where the tip of that one is, I'm going to start drawing R2 right on top of that. So tip to tail, so I start drawing R2 right where R1 ended. And now, if I draw a line from the beginning to the end, from here to here, we're going to get, this is what R1 plus R2 looks like. So this is an easy way to add vector. This is how you can do it visually. No numbers required. If you know what your vectors look like, if you draw them carefully, this can tell you what their combo is going to look like. And I'll go ahead and show you all that it doesn't matter which one I did first. So here I did R1 first, and then I did R2. But according to math, 2 plus 3 is the same as 3 plus 2. So if instead I do R2 first, and then I do R1 second, I didn't draw these as carefully, but it's close enough to get the idea. We can see then when I draw that R1 plus R2, it's the same. Again, roughly. I didn't draw it super precisely, but this is close enough to that you can see it's the same. Order of math doesn't matter. Okay, so this is a really handy technique. Really great way for you all to check your answers. And there will be some questions where I ask you, hey, here's 2 vectors. Show me what the third one looks like. Case in point. Here's a question where there's 2 vectors. Show me what the third one looks like. So, I'll go ahead and start this up. I'll explain the problem. If I add the following 2 vectors, A and B, so A is pointed down and to the right, B is pointed up and to the right. If I add those 2 vectors together, what is going to be the net vector? What's going to be A plus B? What's it going to look like? Answer A is it's going to point to the right. Answer B is going to point to the left. Answer C is going to point down. Answer D is going to point up. Now, regarding quicker questions, I did post the points. I'm doing air quotes here because I posted the points from last class. Remember, I'm not going to start counting the points. Will we address it Wednesday of next week? Start with that. All right. I'm not going to start counting the points for your final grade until Wednesday of next week, so it's coming Wednesday. But I am posting the points now just so you can see whether or not yours is working, whether or not yours is connected and registered. So if on Wednesday it should have been working and you have a dash or a 0 points, you think you should have had some points, that's an indicator that something with registering didn't go right. After today, sometime between now and Wednesday, I won't see you on Monday, I'll do the same thing. Reminder, we don't have class Monday. It's Martin Luther King Day. So, if you show up here, you're welcome to. I won't be here. All right, we'll go for another 10 seconds. So we'll go till 15. So the key to this is drawing it out. 5, 4, 3, 2, 1. All right. So we're going to do this exactly the way I just said. Doesn't matter which one we do first. You know what? I'm going to do B first, just to be spicy. All right, so there's B, up and to the right. We'll draw it a little nicer. Doesn't really matter too much. So B is up to the right. Then A, tip to tail. I start drawing it there. There's A. And we see our net vector is off to the right. Ta-da. Good job, good job. All right. Now I'm going to point out something here. Y is it directly to the right? A was kind of down, B was kind of up. What's happened here is A went down, B went up. So we're going to learn when we start adding components that we add the x components together and the y components together. But we see some symmetry here. So A is going down, B is going up. The up downs cancel because as much as A went down, B went right back up again. You can see that visually. And so the net result is just the right directions matter. Symmetry is a very important thing to look for in problems because it can make your life a little easier. If you recognize that the up down is going to cancel here, that immediately kind of gives you a sense of what the answer is going to be. Still work through it, but then it gives you a sense of whether or not you're right by the end of the day. So by recognizing symmetry in problems, it can kind of give you little clues on whether or not you're doing things correctly. All right. Adding up numerically. This first bullet point's in all bold, all caps, because, so let's just read through. You cannot just add vectors by adding their magnitudes because direction matters. So, if I have a vector that's a value of 3 and a vector that's a value of 5, it is not guaranteed. In fact, it is very unlikely that if I add those vectors together, the new one will be 8. The only way, and I'll show you, so the only way that you can add them super nicely is if they're pointed in exactly the same direction. So sure, if this one's 3 and this one's 5, great, that'll add to 8. That is a very, very, very specific case where they're pointed the exact same direction. It is almost guaranteed that your vectors will not point in the exact same direction, in which case you have to do extra work. So this is why vectors are not the most fun thing to work with, just because they have a bunch of math steps involved, but it's a necessity. There's no getting around it. So to get the quantitative answer, meaning to get a numerical answer, we need to break the vectors into their x and y components to add them. And a very important thing that we're going to see here, and it's going to be true of all physics, and be true of the rest of any science you all do, engineering, stuff like that, x and y are going to be independent. That's going to be a theme throughout this class. Whatever happens in the x, we treat separate from whatever happens in the y. We treat separate from whatever happens in the z. So we treat them all separately. The only variable that continues across all of them we'll find is time. Time has no dimensionality to it. So we'll see that when we get to 2D motion. But I just want to mention the now because it's such an important idea. X, Y, Z, once we break them into components, they do not interact with each other. They do not interact with each other. So we'll see examples of that and it'll be more clear. All right, so adding vectors numerically, we have an example here where we kind of have some visuals. So there's no numbers here, but I just want to show you visually kind of what's going to happen. So we're going to take, I told you we had to break them into their components. So vector A, we need to break that into its x and y components. How do we do that? We make that triangle. So the x component of A is going to be down here. The y component of A is going to be to the right side of it. So we got our two components there. We're going to do the exact same thing with B. B, we're going to make a nice little right triangle here. The x component of B is right there. The y component of B is right there. And it's pointed up. Direction here matters. So for me to numerically add it together visually, excellent. This is exactly what it's going to look like. But if I wanted to figure out, so R, we defined R as A plus B. If I want to figure out how big R is, first I have to find Rx, the x component of R. How do I find that? Well, if we kind of look at the R, we see the big old triangle here. So R makes that a bigger triangle. We'll use blue for that one and kind of do it off to the side. So if we kind of look at R, it's a little tricky because I have to draw on top of these. This is going to be the x component of R, and we're going to see that this over here is going to be the y component of R. Well, I'll put that line actually in a better spot. I'll put it on top of the other one. And if we look at our picture, now by drawing all of this, remember pictures are super handy in physics. If we look at our picture here, we can see that Rx is going to be the x component of A plus the x component of B. We can see this plus this gives us that. So Rx is going to be Ax plus Bx. We look at the y component, and we see if we take the y component of A and the y component of B, this and this make this big old arrow here. So conceptually, that's kind of why we do this. So we have Ry equals Ay plus By. And now, if I want the magnitude of r, we have a triangle. We have the bottom side of it, we have the right side of it. Remember, if you want the magnitude of r, aka how big this side is, the hypotenuse, we're going to do the square root of rx squared, not square root of rx squared plus ry squared. Pythagorean's theorem. Okay? Clearly you all can see there's a good amount of steps here. Vectors just take a bit of time. It's just the reality of it. But it is necessary. We have to break things in x components. We have to break the y components. There's not really shortcuts to this. We wouldn't do it if we didn't have to. All right. So the next slide is just kind of a prettier version of that. The next slide is, instead of my handwriting, it's the same thing, just in typed. So if that's better for you, if that's easier to read, it's the exact same thing. All right. Okay. Let's try it out. So, if I want to add vector A plus vector B, if A is plus 3i plus 2j hat, plus 3i hat plus 2j hat, and B is negative 5i hat plus 4j hat, what's going to be the combination of those two? Answer A says it's 8i hat plus 6j hat. Answer B is negative 2i hat plus 6j hat. C is 2i hat minus 2j hat. And D is negative 2i hat plus 4j hat. Remember that I hat is in the x direction, j hat is in the y direction. So I is basically equivalent to x, and j is equivalent to y. The nice thing is, this is one of those non-calculator ones. So we'll go about 20 more seconds on this. All right. We're going to go and close this one out in 5, 4, 3, 2, 1. All right. So the key here is just remembering that you need to add the x components together, and you have to add the y components together. So the i's go together, and the j's go together. So if we want the x component of a plus b, we're going to take that 3i hat, so a plus b is going to equal, we're going to add our I hat components together. So the I component, the X component, and I, X, same thing. I'm going to basically be using it interchangeably. X component of that one is 3 plus negative 5. So that's the X component of B. Plus, we're then going to do the Y component of A plus the Y component of J, or of B, sorry. So we added this one, and then we added this one and this one. I's got added together, J's got added together. That's how we solve this problem. So that's going to end up equaling 3 plus negative 5 is negative 2, I hat, plus 6, J hat, and there's our answer. Let's see how we did. Very nice. So you all got that down. Now, if I wanted the magnitude of these vectors added together, that's where the extra step comes in. So this is not asked here, but if I did want the magnitude of a plus b, that's where I would have to do the square root of negative 2 squared plus 6 squared. It's just good to remember that that is a thing that will more often be asked. So initially, I'm kind of asking you all vector notation. It's kind of an in-between step. But more often, when we're calculating real-world quantities, distance, velocity, acceleration, we're going to end up wanting the magnitude. So that's pretty much always going to end up having to do that last step there. All right, and then I got one problem we'll kind of work through together, and we'll be able to move on to 1D kinematics today. So there wasn't really that much more we need to cover, which is nice. And again, it's good because we're missing Monday. All right, so I have a picture here. It's got a couple tugboats. The question says, what is the net force in the following image and in what direction? So obviously I haven't taught you all what force is, but that's okay. You don't need to, it's a push or a pull. We're going to learn more about force in the future, but for now all you need to know is push and a pull. So we got a tugboat. The left tugboat is pulling it up and to the left. There's an angle of 12 degrees with respect to the vertical, and it's pulling it with 5,000 units. We're going to learn that the unit for force is newtons, but for now, since I haven't taught you, we just call it units, whatever that force unit may be. And then I got a tugboat pulling up to the right with 4,000 units, and that one's at an angle of 15 degrees to the vertical. Now, we do see some symmetry here. This one's pulling up to the left, this one's pulling up to the right, so we kind of think, oh, I wonder if the x components will cancel. We're going to have to do the math here to be sure, because these angles are not identical, and the forces are not identical. If the angles were the same, and the forces were the same, that would say, oh, we already know right off the bat the x components are going to cancel, and you can kind of somewhat skip that, but here they don't. So, that's just a thing. So, alright, let's go ahead and work through this. So we got a picture, no need to draw one. I suppose if you really want, we can kind of say, okay, I know I'm going to need to get the x component of this. Let's go ahead and label these, because these boats aren't really labeled, so we'll just call this one boat 1 and boat 2. Makes our life a little easier. And so when I'm talking about forces, because it's force, I'm going to call this arrow here F1, F for force, 1 because it's due to boat 1. I'm going to call this guy over here F2, F for force, 2 because I called it 2. You can call these whatever you want, but we need to do something to distinguish them. So we could have F1x, that's the x component of the force due to the boat on the left, and then we'll have F1y. We can kind of start drawing those because we realize, yep, gonna have to do components. That's just how life goes. And let's make the other one a different color just for clarity's sake. We'll pick purple. How exciting. All right, so boat 2, do the same thing. So we'll call this one F1x and we'll call this one F1y. And this whole thing, thank you, F2. Yep. Be very consistent with your notations. Usually you'll end up catching yourself, but if you accidentally mess up your notation, everything's gonna fall apart. Alright, so, picture, great, step 0. Remember, the 4-step problem solving process. Very important, we're gonna be using it a lot. I'm going to be trying to model that with you all as the year goes on. So, step 0, picture is done. Step 1, write down the givens. So I know that F1 is 5,000 units. Again, we put units because we're just making up. I haven't taught you that the unit for force is newtons yet. So for now, we just say it's units, whatever that unit may be. The angle for 1 is 12 degrees. All right. F2 is 4,000 units. And angle 2 is 15 degrees. Okay. Now, I will tell you all, the way I drew this triangle is not ideal, but it will still work. It is not ideal because if you notice, the angle here is not actually inside my triangle. So to that end, this is a good exercise. This is a good opportunity to point out to you all, if that is the case, we have to figure out these angles. Or we can redraw the triangle. I'll show you all both ways just because you can do both ways. So we either have to redraw the triangle, and that's very simply done. Instead of drawing the right triangle here, kind of the way we've been doing it, instead I could have drawn the triangle like this. That one up, that one there, and you can see kind of some this would be F2y, this would be F2x, and now my angle is inside the triangle and it would have been a little easier to work with. But I didn't do that. So let me show you all. You have to be good at, I say have to, trigonometry skills, geometry skills. These are really important because sometimes the angle I give you isn't the one that you need to use to actually get the, sometimes you have to do some geometry. So in this case, if I look at this triangle, there's a couple ways you can get these angles. One, I'm going to go ahead and draw this triangle over here just to give myself a little bit more room. So I know that this is 15 degrees. I also know this is a right triangle, a right angle right here. Meaning, this angle right here is going to be 90 minus 15. Okay? So this angle right here is going to be 90 minus 15 because I have a right side there and doing that. Okay, so that one's 90 minus 15. That's one way you could do it. That's one way you could get that angle. 75 degrees. The other thing you could do, one of the most used, so in geometry you had to learn a bunch of theorems that had to do with angles. For example, one of them is that if you have something like this angle and this angle are the same, this angle and these angles over here are the same. It's maybe a long time since you learned these. These will come into play at some point in your physics engineering thing. These are very, very handy little theorems. So that's one of them. That's really, really handy to kind of have in your repertoire, in your toolbox. The other one, in fact, I got different colors, so I'll use different colors. All right, so those two are the same. The other one that's really handy, I think I even remember the name because I use it so much, parallel line theorem or something like that. So if you have parallel lines and you have a line that goes through them, this angle is the same as this angle, and then this angle is the same as this angle. So that's another really, really handy geometry thing that you will use at some point. If not in this, fairly confident in this class, I'm heck, I'm gonna use it right now, so definitely in this class. But also in your engineering stuff. Very, very important to be able to figure out if given an angle, how can I get all the other angles from that? So to that end, the parallel axis one actually comes in here. I have two parallel lines right here with a line going between them. So that means that this angle is the same as that angle. So I have a parallel line here and here. So this 15 degrees, this is also 15 degrees. Right? So I did a whole bunch extra work here. I did not need to figure out quite everything, but I wanted to show that to you all because it's gonna come up. This is stuff you're gonna have to do. So when I solve problems, you're gonna notice I take way more time than I expect you to necessarily have to take for these problems, because I'm going to try to give you all these kind of little details to help you solve these. The point of me solving this problem isn't to give you all the answer. That's already in the problem set solutions. The point is to show you all the ways to solve it, how to think about it, all that jazz. So yeah, my explanations are going to be a little bit more drawn out than maybe some of you may like. Who knows? Feel free to tune me out at any point. So, to that end, now we get to choose. And in fact, because I want to be difficult, I'm going to use this angle up here. I say difficult because I want to kind of prove a point. I'm going to use that 15 degrees up here. So I am going to choose to use this 15 degrees in my triangle. So that means this is 15 degrees. That means that this is 12 degrees. I will somehow, some way write those numbers. Nope, those aren't going to fit. 15 degrees. 12 degrees. So those are the angles I'm going to use. That's really, so I chose those, which means, all right, we need to add up these forces together. In step one, I'm just going to go ahead and break my vectors into their components because I know I have to do it eventually. So step one is kind of the place to get all your givens, and that's just what I'm going to choose to do. Do wherever you want. Anytime you have vectors, you're going to expect to do that. So, to find the x component of F1, to find this bottom component, we have a right triangle. We have a right triangle. Actually, let me copy and paste. At this point, I'm going to copy and paste this to a new slide. Another recommendation I have for you all is take as much space as you need for a problem. So on the test, whenever we have our midterms, when we have the free response problems, I am going to give you all an entire sheet of paper to show your work for a single problem. The reason for that is if you're trying to cram all your work into a tiny space, it pays to be organized. Let's just put it that way. Ultimately, you need to be able to read your own work, especially if you look at it in the future. And so it pays to be organized. It pays to give yourself the room you need to actually see what's going on here. So again, just little technique, little recommendations here and there that'll kind of pay dividends in the future. All right, so F1x. Let's go ahead and draw the triangle for F1. Again, being really careful here. As time goes on, I won't be as careful on this as we get better and better at vectors. So here's my triangle. 15 degrees, F1, F1x, F1y. I want you all to spend a few seconds. I'm going to straight up tell you we're going to multiply the hypotenuse times either cosine theta or sine theta. Yeah.
Maybe F2 for 15.
Did I put the, oh, thank you. Good catch. All right, 12 degrees, thank you. That's going to save me some heartache later. We're going to go ahead and multiply this times either cosine or sine. Spend a few seconds and see if you can figure out what the right one we're going to use is. Are we going to multiply F1 by cosine of theta, or are we going to multiply F1 times sine of theta? Just think about it in your head for a second. If you said sine of theta, you did a good job. This is going to be F1 times sine of theta. Why is it sine of theta? Because x is opposite my angle. SOHCAHTOA. Sine is opposite over hypotenuse. F1x is the opposite of this angle. So I mentioned to you all previously that very often the x component will be cosine, but I also told you don't get in the habit of that, because you can have problems like this, where the angle is different than the one you might expect. So go through the steps. SOHCAHTOA, opposite over hypotenuse. Opposite in this case is the x component. Therefore, the y component is going to be F1 times cosine of theta. 1. So we plug in the numbers, 5,000 times sine of 12. Make certain your calculator is in degrees mode. That's another way that you can make a silly mistake. Times cosine of 12. I can almost guarantee you all at some, well, I don't know, depends on what classes you take. Calculators can be in degrees or radians mode. Very important that you know how to switch between those if you don't already. So we should get, oh, almost forgot a 0. This is another good technique. I plugged into my calculator and I got 103.956. I looked at that and said, that's too small. How did I know it's too small? Because I started with 5,000. I shouldn't be getting something that small. Again, it's all these tiny little things you can do to catch mistakes. Because when it comes to a test, no one's going to do it for you. Thankfully, I have you all during class to catch my mistakes. But during a test, that's not going to, I won't be go around and helping you all identify those. So anything you can do to reduce mistakes is worth doing. All right, so the next one, 5,000 times cosine of 12. And that's going to come out to 4,890.74 units. All right, and then we repeat the same exact thing for this triangle for F2. So that one is 15 degrees. This one is 4,000 units. So we'll go ahead F1, F2x. Same, the triangle, the angle's up there, so I'm not going to kind of explain that again. F2x is going to be 4,000 times sine of 15. Same exact process, just different numbers. F2y is going to be 4,000 times cosine of 15. So that one's 1,035.28 units. It's a hypothetical unit that I haven't given you before. And then the other one is going to be 3,863.7 units. All right, a lot of setup, but honestly, this is kind of the hard work is done now. The rest of it's fairly simple. So step 1, spend a lot of time on it, but we won't have to write as much for the rest of it. So we're trying to find F1 plus F2 equals question mark. Step 3, to add vectors together, you add the x components, you add the y components, and then we'll have to do the whole Pythagorean's theorem. So, through the beauty of being able to shrink things, actually I'm just going to take this at this point and make a new slide. Take what I need. All right. So step 1, givens. Step 2, what am I solving for? Step 3, what's the equation? How do you do that? To get to add those together, we're going to add our x components. So we're going to do f1x plus f2x equals, we're going to call this f net x. That's kind of some, net means total. Net means total. That's just a math term. We're going to see that a bunch in this class. Then we have f1y plus f2y equals f net y. And then to get f net, meaning just the entire thing, the magnitude, the total shebang, we're going to do Pythagorean's theorem right there. So that's the last step. But at this point, honestly, the math isn't too bad. But you can start to see why vectors are so fun. All right, so we'll go ahead and do those. So to get f net x, that's going to be 1,039. Oh, yes. So I caught myself there, and someone else also caught me, which is perfect, because when we're adding vectors, I mentioned this before, when you get these numbers, these do not have direction to it. So very, very important thing to catch. If I went ahead and added these vectors, so I went ahead and added up the x components, they wouldn't cancel out. They wouldn't cancel out. And that was kind of the red flag in my mind that I kind of paused real quick, and what also someone caught. If this one's going to the left and this one's going to the right, they shouldn't be helping each other. So this is where we need to remember. To the right is positive, to the left is negative. Up is positive, down is negative. So, to that end, I'm going to go ahead and kind of chalk those. So the only one here that's negative is f1x is going to be negative. And so even though the math didn't tell me that this is negative, just to make my life easier, what I may have done when solving this is chucked a negative in there now. Even though the math didn't say it, I'm like, okay, I know there should be a negative here. Or I could have either done it there, or I could have done it here when I realized f1 was to the left and it was negative. So anyway, so yes, we need to put a negative here because it's to the left. It is pulling to the left, and as usual, I didn't give myself enough space. That's going to happen with these vector problems as I have to write out all this jazz. All right, plus 1035.28. I accidentally touched the thing and it angered. That was just that touching the input there. Yeah, cool. Where you put in. Well, that'll give me time to solve it. Negative 1039.56 plus 1035.28. So if you'll remember at the very beginning of the question, I mentioned that they could cancel, but we're not sure. They almost cancel, but not quite. So close. So close. F net y, both of those pointed up. So if you remember back to the picture, they both pointed up. Up is positive, so we can just add those. Neither one's a negative. So 4,890.74 plus 3,863.7. That's going to equal 4,890.74 plus 3,863.7. There is a lot of numbers here that are very specific, so I'm taking my time and making certain I plugged them in correctly. All right, 8,754.44. And then I look at that number, see if it makes sense. Yeah, that makes sense given that. That's another thing. Does your answer that comes out of your calculator make sense? That's a way to check if you fat fingered the wrong thing. Okay, we got the y component, we got the x component. Now we can finally do the square root of these things. So fun. Negative 4.28 squared. It's really not going to do too much to the thing, but we still got to put it. In the grand scheme of things, it's not going to change the answer too much having that x component because it's so small. But still got to do it. Do our due diligence. All right, and as predicted, it did so little that the number didn't, my calculator to 2 decimal places, it didn't change it to the second decimal place. So it ends up looking like the same number, and that's just because of rounding. So that's just a good thing to point out here. If you have an x component that's itty bitty, and this one's really big, approximately, we can almost pretend like this one doesn't exist. Mathematically, when we do rounding to 2 or 3 decimal places, it doesn't really do anything. If you're like, what happened here? That's just because it's so little in comparison. When you do the math, rounding it out, it disappears. Maybe it affected like the 3rd or 4th or 5th decimal place, but who cares? All right. We did it. Great job, us. Vectors. Something I will try to do. Oh, yeah. What direction? So in this case, we can also the x component's basically canceled. So the resultant vector, we could figure out the direction just by doing visual adding. In fact, I generally kind of recommend that. This one's basically going to be straight up. We could so if we made this triangle, there's no way I'm going to be able to draw this triangle to scale. The y component is 8,754. The x component is negative 4.28. That is clearly not to scale at all. So technically, if I kind of draw this little thing here, technically there's a little angle there, but it's basically 90 degrees straight up in this problem. So technically you could do tangent inverse, it's going to spit out. I'll let you all do that for yourself. We'll say that this one is pointed straight up, or you could say it's 90 degrees with respect to the positive x-axis. Positive x-axis. I'm not going to really worry about that too much. If you have questions about that, feel free to ask me at some point, but straight up. All right. So something I'd like to do, I try to do my best to remember this, is at the end of doing any big old bunch of thing like this, at the end of kind of doing a unit, I want to kind of give you all, hey, okay, we did a bunch of things. What's the main things to take away from this entire thing? So main takeaways. Don't forget your units. So I already put that before. This is just reminders of the key takeaways from the entire thing. Don't forget your units. Every single answer should have a unit after it. And that unit defines what it is. Make sure your numbers are in base units. Meaning, if I have centimeters, convert it to meters. If I have millimeters, convert it to meters. If I have grams, convert it to kilograms. Kilograms is the weird one. Anytime your unit basically has more than one letter, you need to convert it so that it only has one letter. It's kind of a good rule of thumb. Mass is the only one that kind of breaks that. Vectors have direction and magnitude, which matters a lot. So they have a direction and how much they are. And then the last thing we kind of just saw, when adding vectors, you have to break them into components. These are the main 4 things that we kind of covered in this, and the things you need to know and you need to be doing in your problems. This is how we do physics. You need to have units, you need to make sure your base units, vectors have direction and magnitude, and you have to break things into components, i.e. x and y component. Blessings for you all is you don't have to deal with z. But technically in the real world it's 3 dimensions, so we would actually have to break things into x, y, z, you'd actually have to add in. So in that last problem, if that was 3 dimensional, we would have to do that for z as well. And that gets real fun, because break fun is clear sarcasm, hopefully. When you're breaking it into x, y, and z components, you actually have 2 angles you have to work with, and it's worse. So, fun fact for you all. Alright, so we only got a few minutes. I am going to start the vector stuff, so I'll go ahead and save this one so that all my hard work that I put into these slides isn't disappeared. I'll upload these before I leave this room, before the end of, well, after the class ends, I'll upload them. So if there's anything up there that you're like you didn't copy down, or anything you're confused about, or whatever. But I am going to start talking about 1D kinematics, because again, we got to because we're losing out on Monday. So 1D kinematics, I know what's on the slide, so I'll just start talking about it while my computer struggles here. 1D kinematics is going to be actually getting into physics. Everything I just taught you all was math, with the exception of units existing, you have to do base units. This math is important. We need to know this math. It is foundational to us solving a ton of problems in this class, so we had to spend the time on it. And we're going to get lots of practice with it in the future. But next week, once you get kinematics, this is where we're actually getting into physics, the world. And we're going to start, so in this class, we hear about moving things. So we're going to start with what is movement, what is position, what is very basic things. A lot of this is going to be simple with the caveat that there's going to be some things here that are going to be kind of weird to us. I'll show you what I mean when I say that. For example, displacements. So we're going to talk about displacement. So I walk in a circle, and I end back where I started, and I say, what's my displacement? It's 0. So if you've taken physics before, you know it's 0. Displacement, we're going to find, is this weird thing. It's not how far you travel, it's how far you're located from where you started. So again, there's some weird stuff that's going to come in, and it's going to be important that we have these distinctions between displacement and distance. But we'll get into that. So, we're going to talk about common measurements of moving objects. There's a lot of moving things in the world. If you're in engineering, you're going to be working with a lot of moving things, assuming you're mechanical, aerospace, civil. Well, civil, ideally you don't want things to move, I suppose, generally. Or maybe you have moving things, probably. If you're computer engineering or electrical engineering, still good for y'all. The kind of foundational stuff here. So position, velocity, and acceleration is going to be our bread and butter for this. And we're going to kind of figure out how to calculate them given the other ones. So if I give you position and velocity in time, find acceleration, pick 3, find the 4th. And we need to be able to interpret graphs, because graphs are very good. Graphs show 1,000 data points is kind of the comparison. So a picture says 1,000 words, a graph shows 1,000 data points. So we'll kind of define a couple things. So kinematics is the fancy word that basically says study of an object's motion. So you're going to use the word kinematics a lot. That's just terminology when we study moving things. We don't care why they're moving, we just care they are. We're going to learn why things move when we get to Newton's laws. And yeah, we need these precise terminologies: displacement, velocity, acceleration. So we're going to use displacement, not distance. We're going to use velocity most commonly, not speed most commonly, because fun, they're vectors. Direction matters. We're going to see that displacement is a vector, distance is not. Velocity is a vector, speed is not. All right. So, position. This is where you're at. Position is where you're at. And it's a vector. So, position is an object located relative to a reference frame. Reference frame is a really fun bunch of jargon that most of you probably haven't heard before. Reference frames are really, really important. Reference frames are what you reference yourself to. So, for example, if I asked you right now, where are you located? It's a great, relative to what? Relative to me? Relative to your seat? Relative to the top of the classroom? Relative to my desk? You have to have a point that you define as 0. If you don't have a place defined as 0, you can measure your position to be anything. And in fact, it is anything until you define that position. So in the front row, they're about 4 meters from me, but they're about 7 meters from the door, about 8 meters. And not only is the distance bigger, but the amount. So anyway, it's very, very, very important that you have a reference frame. Where is position located from? It's like telling your friend, I'm 5 miles away. From what? When we get to velocity, the same thing is going to be true, but we'll save that. All right, so unit is meters. Really straightforward. It's what you hopefully expected. Not miles, even though I just said miles. Miles is trash. Meters is better. Remember, converting metric units is superior. And we're going to use the variable r for position. R, because we have x, y, and z, makes it all up. R includes all of them together. All right, so the last thing I'll put up here, we have position, and the one more commonly we're going to use is displacement. Displacement is literally just take 2 positions and subtract them. I went from this position to this position. That was my displacement. So, R, but it's a change. This is delta. This triangle here is delta, that is change. So, your displacement is your change in x, I hat, plus your change in y. J hat, plus you're changing Z, K hat. Again, for you all, we're really only working with I and J. In fact, in this presentation, we're just going to work with X. We'll build to 2D. That'll be the week after next. So there you go.